So when we go to find the average atomic mass, it's very similar to this little example where if your semester grade's 60% exams, 40% labs, your exams will affect your grade more than a lab because there's a higher percentage. And so the average would probably be closer to your exam score grade than your lab grade when you get your semester grade. Or if you think about a bag of marbles, let's say you have 5 1-gram marbles, but you have 1 10-gram marble. The average going to be right in the middle, 5.5? The average mass? If I have 5 1-gram marbles and 1 10-gram marble, would the average be 5.5? Right in the middle? Weighted average? No, it should be closer to the 1. Right? Because there's more 1-gram marbles. Yeah. So that's what we will do when we get to the average atomic mass. We will look at the isotopes, atomic number, and be able to figure out how many protons, neutrons, and electrons. The second part of the section we will look at next week. The moles. We'll talk about the moles next week. So the atomic number is the number of protons. And we already talked about how atoms of the same element have the same number of protons. That's what gives it its chemical identity. And the atomic number is represented by the letter Z. So if you see a Z equals 34, you know that you have element selenium. That's your element that you're using. And that is equal to the number of protons. And the periodic table is arranged according to the atomic number. So as you look across, it was 1, 2, 3, 4, 5. Those are the atomic numbers, and that is equal to the number of protons. So you can find your atomic number on the periodic table. So here is your atomic number. For oxygen, it is number 8, and that means there are 8 protons in the nucleus. Isotopes are atoms of the same element that have different masses. So since they're the same element, that means they have to have the same number of protons. But what is the other subatomic particle that contributes to the mass of an atom? The proton and neutron. The electron, remember, is so small that we don't include it in the mass. So to have different masses, it has to have a different number of neutrons. It has the same number of protons, different number of neutrons. Most elements consist of mixtures of isotopes, except for some of the man-made ones, like down by 89. It's about 89 to 112 or 115, because they're smashing those atoms together, and they're really only making one isotope of that atom. They aren't naturally occurring. The mass number is the number of protons and neutrons. So when you add the protons plus neutrons, that would be your mass number of that isotope. So all the isotopes will have different mass numbers. They all have the same atomic number, but they have different mass numbers. So here, what would the mass number for this isotope of oxygen be? If we add protons plus neutrons. I hear it, I think. 16. 16 would be our mass number. Now, if this is on the periodic table, do you see 16 anywhere? No, you cannot find the mass number on the periodic table. This number right here is its average mass. And it's really close to 16, which means that most of the isotopes are probably oxygen 16. Most of the isotopes have 8 neutrons, but there are a few that would not, and that's why the average mass is not 16. And there's 2 different ways that we can write out the isotope. And the first is a hyphen notation, and it's the mass number written with a hyphen after the name of the element. So you have uranium-235. The 235 means that there's 235 protons plus neutrons. It's the mass number. And then the nuclear symbol, the superscript would be your mass number. So this top number is your mass number, and the bottom subscript would be the atomic number. So what you need to be able to do is look at these isotopes and tell me how many protons, electrons, and neutrons are there. So how many protons are there in this uranium-235 isotope? No, this is the mass number. No. Number of protons is equal to which number? The atomic number. So what is uranium's atomic number? 92. You could either, if you were just given the hyphen notation, you'd have to look up on the periodic table. It's element 92. But since we have the nuclear symbol, it's given to us right here. So how many electrons? It's neutral, right? Protons have to equal electrons. And how many neutrons? Mass number is protons plus neutrons.
143.
So you'd have 235 protons plus neutrons, and you know there's 92 protons. So you subtract them. You get 143. We'll do another example of this here. Oh, this goes through how we would solve for the protons plus neutrons. And this is just a term, we won't really use it. I won't use it very much, but the nuclide is just a specific isotope, but you might see it in your, like in the chapter review on our worksheet. But basically, the uranium-235 is one nuclide, and then uranium-238 would be a different one. Just saying it's a different isotope. Okay, how many protons, electrons, and neutrons are in chlorine-37? So how many protons, electrons, and neutrons?
No.
17 protons.
Come on, Sarah, do that math in your head right.
How would you find 17? Where do you need to look?
Look right there on that periodic table.
Periodic table. Remember, 37 is your mass number, which is protons plus neutrons. So you have to look up the number of protons. How many electrons would there be?
17.
And then how many neutrons? Right. So neutrons would be, the protons plus neutrons need to equal 37. You guys want to go through another example?
One more.
One more?
Uno más.
I don't know.
Carbon 14.
Let's pick
Hydrogen.
10, 120.
So it'd be 50 protons.
Yep, 50.
50 electrons. 70 neutrons.
Does everyone understand where we get that? So look up 10. 10 is element number 50. So that means there's 50 protons. Protons and electrons have to be equal since it's neutral. And then the protons and neutrons added together need to equal the 120. And I don't know if that's actually an isotope. I just picked a number. Carbon 14 is, yes. Okay, and then I think 120 minus 70. Or 120 minus 50, yeah, equals 70. Yeah. Okay, this goes through the solution that we already did. And the last part for today, the relative atomic masses. This is all just saying basically, instead of writing all that word for word, that the atomic mass unit is equal to 1/12 the mass of carbon-12. So when you see that sodium average mass is 22.98977 AMU, that means that one of those AMUs is equal to 1/12 of copper or carbon-12. It's just how they are able to make a standard. That's their standard for a mass unit. AMU is just atomic mass unit. And we'll see whenever we get to grams or the moles that we can either call those AMU or grams per mole. Those units are interchangeable. We will use grams per mole a lot more. And to find the average, the weighted average, which would be on the periodic table, those are the masses you see on the periodic table, you have to, it depends on both the mass and relative abundance. So you want to take the mass of isotope 1, and you would multiply it by I'm going to call it just Ra instead of writing out relative abundance. Relative abundance of isotope 1. Relative abundance means it's in fraction form, so instead of saying 69%, it would just be 0.69. Okay, and then you would add that to, take the mass of the second isotope times its relative abundance, plus the mass of the third isotope. There can be many, many isotopes. And you would just keep repeating this until you've done all of the isotopes that are listed. Yes, it needs to be in decimal form. So there's percent abundance and relative abundance. You want to use relative abundance, not the percentage. It will probably give you the percentage, but you need to convert that. And what should if you add up the percentages of all the isotopes, what should they equal? If it's all of the isotopes, 100 should equal 100%. So sometimes they won't give you each one. Maybe they might leave off one, but they should all equal 100. You should be able to solve for that. So let's try this example. Copper. So here's, in this problem, they give you the actual AMU mass. But if they wouldn't give you that, go ahead and use 63. That's close enough to the actual mass that we can use that. But since they give us the actual mass, let's use that. So what's the mass of the first isotope?
62.929.
Times, what's its relative abundance?
69.15.
Mm-hmm.
No, I don't know.
Right, we got to change that to decimal form.
Yeah.
Plus, mass of the second is right here, so 64.4 times its relative abundance would be 0.3085. This number? Right here. Now, while they're calculating this, let's just think about what the number should be. It should be between the 62.929 and 64.927. So if you get an answer of 23, is that right? No. Okay, you need to have it in between those two numbers. And then which one should it be closer to? Which one has more naturally occurring isotopes? The first one, right? There's 69% of that versus 30. So it should be closer to the one that has the most isotopes. And what do you get?
How about 63.54604.354?
We'll just leave it like this. Because really, and they'll show it, we should round it right here. Based on significant figures, since we have 4 significant digits here, we should have just 4. Use that.
Good call.
Very good. So I do have, this worksheet's due on Thursday. Thursday because you're doing pictures and everything, and the other periods, who knows, I don't even know if they're going to be around. And you're doing bus evacuations tomorrow. So this is due Thursday. The front, you just have to write out the number of protons, electrons, and neutrons. The back, basically the same information, is just in a chart, but you have to make sure, based on this information, you should be able to find what element it is. And the nuclear symbol, remember, nuclear symbol has the mass number over atomic number with the symbol. You need to have the nuclear symbol here, where it had the mass number. So it was like the uranium one was 235 over 92U. That's the nuclear symbol. And then fill this out. The bottom, very last one, a problem just like that. We just have 3 isotopes instead of just 2. Okay? So the bottom one is just like that.